Hello everybody, my name is Martijn Schootstra and today's lesson is all about batteries for off-grid solar systems. I'm an engineer. I've studied mechanical engineering in University of Delft, and after that I worked 12 years for Unilever, an international career mainly in engineering and production, and I was responsible for the construction of a greenfield factory, cosmetics factory in France. For over 15 years, I'm now active in solar energy, initially in the Netherlands with a startup company installing mainly grid-connected solar systems. I was subsequently a board member for the Dutch trade organization for the solar industry called Holland Solar. I've been an auditor for a quality certification scheme for these solar installers in the Netherlands. And more recently, I'm advisor to FRES, an organization active in rural Africa. And that is all off-grid solar systems, so with batteries. So I'm quite heavily involved in specifying and purchasing batteries for either mini grids or smaller solar home systems. I will talk about different battery types, the lifetime of these battery types, how to compare them, and particularly when you have to purchase batteries. And I have some comments about how you use them in practice. And lastly, I will talk about lithium batteries, and that means that actually the majority of the presentation is all about lead-acid batteries. Well, to start immediately with some comments here, batteries are incredibly important in an off-grid solar system. When you buy a new system, then often the batteries represent about half the cost of the total system. And over the entire lifetime, the costs are even higher because the batteries, they have the shortest lifetime of all the components, typically 4 to 6 years for good batteries, but much shorter even for cheaper batteries. And what's very sad about it is that the more you use them, the shorter they live. And that makes the batteries and off-grid solar systems, I would say, at least twice as expensive as grid-connected solar systems. So when people say solar energy is now cheap, that is correct for grid-connected solar, but for off-grid systems, that is a different case. Now, if we talk about batteries, then the first question is always, what should we buy? And then, of course, manufacturers all around the world, they claim that they have the best battery, but it's not so easy to compare that because, of course, it's an invisible chemical process in a closed box, a black box, and we have no clue what's happening inside. And all the manufacturers, they say that they have the best technology and so on in advertising. So part of this goal of this lesson is to give you some insight where to look at when you purchase these batteries. Now, to give you the answer straight away, and of course we'll zoom into that later on, but lead-acid batteries are still the most common, and particularly in Africa and India. And of amongst the various technologies like AGM or gel and so on, there is no clear winner. We cannot say upfront, outright, you should go for one or the other. It all very much depends on the actual battery and the performance. And then we'll zoom in where you should look for in detail. Lithium iron phosphate batteries, they're becoming competitive, in particular for smaller solar kits and solar lanterns, but also for larger systems. And it's simply because they're becoming cheaper over time, whereas lead acid has not been declining in prices as much. My recommendation is to compare the batteries on the basis of a cost per cycle, and I'll explain that, how that works. And there are many other storage technologies being developed, but often they're not suited for solar. They're more for automotive, like for cars, or for lightweight situations, like for your phone, for instance. Or they're too complicated, or they're only suited for very big systems, or they're not even cheaper. So for now, lead acid is still the main battery for applications for solar energy, and emerging is lithium batteries. Now, if we start with some terminology, then the most important one to know is called the depth of discharge. And that is indicated with the red arrow. So if you discharge a battery, let's say over time, say in this case, I would say 15% of energy has been used. And that means that the depth of discharge is 15%. Now, that also implies that is the inverse of this, that is depth of discharge, and that's called state of charge. So that is actually, that's the green arrow, and that means in this case, if the depth of discharge is 15, then the state of charge is 85%. For lead acid batteries, we will see later on, we usually do not discharge deeper than 50%. I have another chart to show that, and here you see depth of discharge 0% on the left-hand side, state of charge therefore 100%, and as we see here, if we go towards the right, the depth of discharge is increasing, and the state of discharge as well. So you see here the right-hand side, it's both 50%. Another terminology is called state of health. And the reason is that batteries, they age over time and they lose capacity. So a new battery, when you purchase a new battery, the battery is still 100% state of health. That means the battery is functioning as new. But as time progresses, then the battery will have lost time and capacity. And you see that here in the red block at the bottom. It's actually permanent loss of capacity. And the state of health is actually, it's just a percentage, is the current battery capacity in relation to its original capacity. For instance, if the state of health is say 80%, that means that we have lost 20% capacity already, and that the battery we can still use 80%. Now, it's actually difficult to measure this. It's not that you can take a reading with the voltage meter and say, oh, now this battery is so good and so on, or is new. Unfortunately, the only real way to do it is to apply a load and measure time, voltage and current, and calculate the amount of energy that battery contains. That is the only way of doing it. And that is, unfortunately, is a very time-consuming aspect, particularly if you have to test a lot of batteries at the same time. The C rate is often indicated. People will say that if you discharge this battery at C10 rate, then you need to know what that means. It's actually the rate at which the battery is being discharged, and that the X stands for the time in hours. So the best is to look at that, the two examples mentioned there. So the C10 rate is the current will discharge the entire battery in 10 hours. So if it is an 80 amp hour battery, then divided by 10 hours, that is a current of 8 amp. C20 current, for instance, is discharge the entire battery in 20 hours. So if, imagine we have a 100 amp battery divided by 20 hours, that means it's 5 amp. Now, to make it a bit more confusing, sometimes people do not write C10, but they write 0.1 C or C/10. And if it's C5, it's even more complicated. It's 0.2 C and C5. So unfortunately, this is a real life practice. Now, this graph shows you the lifetime of a battery in the number of cycles. So on the vertical axis, you see the number of cycles, up to 7,000 cycles, the lifetime. And on the horizontal axis, you see the depth of discharge, the DOD, as we mentioned earlier. And as I said, we should not discharge deeper than 50%. So that's why I put a red arrow here. The different lines are for different temperatures. So the top line, the blue line, is for 20 degrees C, and every line further on, it is an increase by 5 degrees C. So and the bottom one is 45 degrees C ambient temperature. So what is important to draw from this graph? Well, that if we have a battery and we use it only up to 20% depth of discharge, then the lifetime is significant. I mean, 6,000 cycles for this particular battery. I must say this is a very good Hoppocke AGM battery. Then it's almost 20, you could say it's 20 years. Now, this is an expensive way of using a battery. Usually you design a system more for depth of discharge of, say, 30 to 40%. And then we're in this range, say 3,000 to 4,000 cycles. Now, if that same battery is operating in a hot climate, then you can see that the number of cycles is then much lower. That is very unfortunate, but it's a fact of life for lead-acid batteries. So those are the drawbacks. I mean, I put here at the right-hand side the number of cycles in years. Imagine if that battery is being used every day up to this charge. So the difference here between, say, 25 degrees will be, say, around 8 years, and if it's 35 degrees, then it's let's have a look. That's more like 6 years. So you see that effect of temperature. Now, as I mentioned, there are different type of lead-acid batteries, and here are some main examples. AGM, that's a situation where the electrolyte, which is in that battery, this is a closed battery, absorbed in a glass mat that holds the electrolyte together. Gel battery is slightly different. That the electrolyte is like a gel. It has some advantages. For instance, a gel battery they claim performs better in high temperatures compared to AGM. I must say I'm using for another organization AGM batteries from Hoppocke, and they perform also very good in hot climates. So there you see it's quite difficult to make comparison. Lead carbon is another type that's emerging at the moment. There, the negative plate is treated with carbon that avoids the crystals to stick on the plate. Usually also gel, and people claim a long lifetime. Another type construction is called a tubular plate, and it's not that visible, but in this case you see that the active material is positioned in polyester tubes. that makes that it fixes them in place, and the benefits are so it's a larger surface and therefore more capacity and longer lifetime. They are definitely more expensive than the other models I mentioned, and also they're bigger in size. Because of the tubes internally, there's more space. Typically, they are used for bigger installations, and then and so as I mentioned here, two-fold cells. And then there are two types. One is OPZS, that is a flooded battery. That is usually the clear battery here. You see the actual electrolyte level, which you have to replenish. When it evaporates, you have to fill it. And the other one with a valve, it's called VRLA gel battery. That's the one on the left-hand side. As I mentioned, often they're used in mini grids, these big batteries. And the beauty of this is that you can, particularly in hot climates, if the water has been evaporated, that you can actually top them up. That is not the case with the closed batteries. But of course, they're not maintenance free. So it is not for a small installation. So the gel, as mentioned, is maintenance free. But once you overheat them and you lose capacity, then that's forever. To put it in a different, schematic, here you can see on the right-hand side, the two-fold cells. And you have them at the top flooded, and at the bottom you have them gel. And you can also have them in 12-fold blocks, even 3-fold blocks as well. And then they look more like this. There's another type of battery it is an AGM battery, and that's quite different construction, where the plates are actually spiraled together. The advantage is the battery is extremely strong and rigid, and it has a very large current it can deliver. So it's actually more suited for, say, starter batteries with long lifetime. And they're usually not used in solar installations. Now, unsuitable for solar applications are the so-called starter batteries or a car battery, because they're actually designed to deliver a very high current, but during a very short period, only say 30 seconds and so on. Whereas a solar battery has the same amount of energy, but it is delivering that for several hours. So they are designed very differently. Other batteries that are not suitable are called UPS or telecom batteries, because they're designed not to give actually much energy, but to have a very long standby life, because they are served as backup power, so they're hardly used, but they need to be in production for a long time. But again, not suitable for solar applications. Now, I've mentioned already a lot of names, OPZS, V, and gel, carbon, and so on. It is about confusing, and that's why I made this this table. And the first type is to make sure, are we talking about a flooded battery? Flooded, sometimes people say they call it wet or vented or open. That is one big family name. And the other one are called maintenance-free batteries, or VRLA, valve-regulated lead-acid battery, or SLA, sealed lead-acid battery, or just sealed. So a lot of different words for more or less the same family. Then, as we mentioned, you have the different construction types and build-up. It shows here thin plate, tubular plate, flat plate, spiral. and if the electrolyte is in liquid or in a gel. And my recommendation is to use for solar the types mentioned in this yellow box, and the ones I mentioned before. These are the ones that is most suited for solar applications. Now you will then say to me, okay, fine, but that's not a recommendation. I still see a lot of different technologies. How should we then compare these? Now, and I will handle that in this chapter, and so we can call it battery purchasing. And what's very important actually to make sure that when you buy a battery, that there is a data sheet belonging to that battery. You could almost say batteries that have no data sheet, I would not trust them. The ones that have a data sheet, these batteries are often tested and certified. I put up here at the bottom, you see that the various engineering standards. And if they are, then that gives a much better feeling for the lifetime of the battery. So the datasheet contains not only the weight of dimensions, of course, also the capacity in amp hours, depending on the various C rates and so on, but also the charging voltages, which is important because you have to program your charge controller exactly for those voltages. Now, if we're talking about lifetime, then this chart here will give you the details about that lifetime. And I'll put it here on this next slide. That chart looks a bit like this. You see here the number of cycles on the horizontal axis and vertically the capacity. Now, we often say that we look at the number of cycles until 80%. So the state of health, this is. So the state of health has been reached 80%. And we designed a system for 50% depth of discharge. That is in here. And if you then look at this point, approximately this point, then for this particular battery, you come out at around 2,100 cycles expected lifetime. If you treat them well, of course. So no overcharging, no undercharging, and all these different parameters. But nevertheless, if you look at the data sheet, it's important, and look at this chart, because you'll be surprised. This 2,100 is actually quite high. You can easily find batteries that this number will be, say, 800. I mean, so easily less than half. So that dictates very much of what you're getting, really. Now, as an example is, for instance, in this table here, we have three different AGM batteries, ABC, different companies and different brands. And it starts already that they're not the same capacity. So in this case, we have to look at the C10 capacity. You look in the data sheet and you find the various numbers. So, well, let's say battery C is the biggest, so it's probably the best. Then you look at the prices and you say, oh yeah, but that's an expensive battery, and battery B is actually a lot cheaper, so maybe I should do that. Then I can say, okay, let's compare that to the price in amp hour. So if you divide the price by the amp hour, then you say, okay, but then battery B is again the cheapest, so why not getting that? And then you look in the data sheet and you check the tables and you say that the cycle lifetime is 1,700 cycles, whereas battery C has more, has 2,300 cycles. And if you then do a calculation, I will come to that in a minute, then it actually turns out that the life cycle cost of storage for battery C is actually the lowest. So that is the best buy you can do. So I'm not saying that the most expensive battery is always better, because this battery is also more expensive and it is not as good as the others. But what's really important is the number of cycles. Now, this is how you calculate it. Basically, on the top, I put it here, CapEx. It's actually the price of the battery. And just ignore for the other aspects. And you divide it by the number of cycles out of that data sheet times depth of discharge. But I would say then every time, say 50% or 40%, that doesn't matter. And the capacity of the battery in kilowatt hour. I would say that kilowatt hour because it's, of course, that's voltage times the amp hour divided by 1,000. If we do that, then you get a number, this figure like 12 cents per kilowatt hour, something like that. If we're comparing lead acid batteries with, say, other types like lithium, that's important also to include a round trip efficiency in this calculation. And then you discover that lithium actually is very expensive, but it has high cycle lifetime. And the depth of discharge is deeper as well. So if you do the sums, you will see that that works out quite okay. Now, a bit sneaky, but manufacturers, they advertise, and then, for instance, the capacity, they say this, well, this is at the 1.70 volts end voltage. And other manufacturers, they do that at 1.8 voltage. You just have a look at the data sheet. If you compare that in terms of capacity, there's already more than 5% capacity difference between the two. So a good example is here. There's a Ritar OPZV 100. So you think that's a 100 amp battery. Oh, yes, it is. And it is a 100 amp hour rate at C10 rating. At C20, actually, the capacity is higher. Now, the Hoppeke, they have the battery called 12105, and you think it's maybe 105 amp hour, but if you then look at the data sheet at C10, the capacity is actually 87. So be careful. Look at the data sheets. Get the actual data. Sometimes it's good to look at the weight, and usually. A battery, you have a look at this. Basically, if the battery is too light and there's not enough lead inside, it's unlikely to give a very high capacity. Now, this one I'm saying, make sure that the battery is not older than 6 months' time. Now, this is very difficult to check because it's often not written on the battery, but you don't want to buy a battery that has been sitting in a store for more than a year or so, because the battery will lose capacity if it's not being used. So best is to buy from a store that is selling a lot of batteries. Now, another aspect which is interesting to look at is should I design a system for a large battery that is not heavily used, or for a smaller battery? So here we have, again, comparing 3 different batteries, and in this case, they're all the same battery type and model, but they have different capacities. So A is 87 amp hour battery, and so on. The C is bigger, 133 amp hour. Now the prices are, of course, different. The price per amp hour is also slightly different. That means the bigger the battery, it's actually cheaper per amp hour, as you can see here. But if you then say we need 43 amp hour capacity, that means that the battery A will have to be discharged by 50%. 87 divided by 2 is around 43. Now, if we have a bigger battery, and particularly in this one here, we only have to discharge the bigger battery by 30% to draw 43 amp hour from that battery. Now, if you then look at the data sheets, then the cycle life of these batteries is different. So 50% DOD, that gives us this amount of cycles. And battery C, that is not discharged as much as deep, has a longer cycle life. And if you then do the same calculations as shown earlier, then what's very interesting to see is that it is cheaper to have a battery, a bigger battery, and that is not as used that heavily compared to a smaller battery that you discharge deeper. And I must say this is still within range, but I can imagine if you discharge deeper, more than 50%, the cost will shoot up and the lifetime will be much, much shorter. So of course, one comment is you need to have the money available to buy the big battery, of course. But again, check the datasheet for what's written there. Now, some tips and guidelines for practical use. Charging of the batteries. It goes through various phases. The first phase is called bulk. That means it's actually constant current, and it's actually maximum current in that case. And that the battery will be say charged up to say 80% capacity in a few hours only. And then is the next phase, which is called the absorption phase, and that takes a long time. That's actually a constant voltage situation, and the current drops off gradually over time. Now, the beauty is that the charge controller will take care of all this, so you don't have to worry about it. What is actually disadvantage is that the absorption phase takes a long time, and if I say 10 to 12 hours in total, then of course there's maybe not enough sunshine during the day to reach that state of fully charged. Now, every battery brand and type has different settings in terms of voltages for bulk and absorption and float. And you have to check the data sheet and program your charge controller accordingly, and particularly to avoid, say, overcharging. If you have a charger in general should be about 10% of the amp rating. That also implies if you have a grid charger. So do not overcharge, but also not undercharge. Otherwise, the battery will never reach its full state of charge. Discharging, as I mentioned already earlier, the faster the battery is being discharged, the capacity, actually, the battery loses its capacity. It has a lower capacity. So look at that. Again, when you design a system, that's important. Usually we talk about C10 because we're discharging over the night until 50% DOD. So that this is usually the situation. So don't discharge the batteries, ideally not more than 50%, but preferably even less. And then your charge controller will prevent this, but you need to set the load voltage disconnect settings accordingly, and that depends on the discharge current. So it is a quite more complicated. The good charge controllers will help you with that, how to set these, how to program them. If we have a battery bank, that means we want to increase the voltage to either 24 or to 48 volts. Or increase capacity, so we can either go multiple batteries in series to increase the voltage, or multiple strings in parallel to increase the capacity. Then I must say this is not ideal. and in any case, not more than 3 parallel strings. And the reason is actually, I'll come to that in a little bit in a minute, these batteries should all be of the same type, brand, and capacity, and also age. So you cannot mix old battery, and if imagine one battery fails in a battery bank, then you cannot put a new battery bank, a new battery inside. You have to replace them all at the same time. And I'll come to that in why that is, because basically one battery will be used more than the others. Also important is that the wiring should be symmetrical, the same cable length and the same cable diameter, to make sure that there is equal resistance and to avoid unequal charging and discharging. So that is here are some examples of symmetrical wiring to ensure equal resistance. So on the left-hand side, you can see that you don't want to connect here at the same time, because in that case, this battery has a lower resistance than the batteries that are further away. So if you connect it like this, then the length of wiring for all the batteries will be the same. This is another way of doing it, having all these wires the same length. Here you see the halfway. Again, it's mirrored in such a way that the resistance is the same. Or you have a bus bar with a very low resistance. That's another option. There's actually, Victron Energy has a very nice booklet where they explain all this. That's where I took the pictures from. And this picture also, this is actually showing the situation where you have not equal wiring. So you see at the lowest battery has the lowest, the one at the bottom has the lowest resistance, and that's then the largest current. And all the further batteries are away, the resistance increases and the current is smaller. And that means that these batteries are unequally charged and discharged. And that means that the battery life, the lifetime, of course, will drop dramatically from the big battery, of the one that is used most heavily. Another solution for a battery bank is to you want to make sure that the voltages are the same. So here you see 2 batteries wired in series to create a battery bank of 24 volts. And when you do a measurement, then you discover that the voltages are not the same. And that can be the case due to wiring or either the state and health of these batteries. Now, in order to avoid this situation, it's possible to install a so-called battery balancer that is measuring both on both batteries. And then as soon as the voltage drop is more than 0.1 volt, it will then draw a current to actually balance the 2 batteries. And this will prolong the lifetime of the batteries. Now, to avoid, say, permanent loss of capacity, some recommendations: avoid overcharging. If the battery is empty, then make sure you charge it immediately, but don't leave it discharged just like that. That's very bad. Even if the batteries are full, they will lose capacity, and they need to be charged every six months. And this is important, of course. Even if you buy a new battery, you should charge it straight away. And this is why it is dangerous if you buy from a store and the battery is not has been sitting there, and if you don't know what happened during storage. Even solar batteries, ideally, they like to be charged once a year. during 48 hours, and this is to avoid sulfonation of the batteries. Don't install them in the sun, and the reason is that UV will damage the casing, but also the temperature will be on one side of the battery and disturb the process, the chemical process inside. It will not be equal. In case you have flooded batteries, of course, then you need to make sure that the electrolyte level is always at the same, it topped up. And the flooded batteries should be charged once a month with a higher equalization charge. Again, a good charge controller will take care of that. So that's why a good charge controller is so important. I would say then maintenance, make sure you inspect them, even if there's a maintenance-free battery, check them, make sure they're clean, no corrosion, charge them, and if it's electrolyte, is it a flooded battery, then make sure it's topped up. Then some comments about safety. The electrolyte, that is sulfuric acid, and this is dangerous, so make sure that you use protective gloves and so on. And the lead is highly poisonous. So you don't want that to either in the environment or in terms of your health. And then last but not least, then the battery, of course, contains a lot of energy. So make sure you install fuses or circuit breakers, because if in case of a short circuit, the battery can explode. So isolate the battery before you do any maintenance, and make sure that you use tools that insulated handles. This is it. Recycling lead acid batteries. Often people are critical about it because lead is so poisonous. But recycling of lead is very much possible, and a recommendation is to sell the batteries to a professional dealer, because they will take care that the battery is being shipped to a professional recycling industry. Now, some comments about lithium batteries. There are different types of batteries in cars, and in your phones you have different lithium, but for solar, the so-called lithium iron phosphate battery, or LFP battery, is the technology that is ideally suited. They're actually not as lightweight as the ones in your phone, but they are much better because they're also they have a long lifetime. Now, compared to lead acid, there's several advantages. You can discharge them much deeper, and DOD can be much deeper, up to 95%. They're very good suited to high temperatures. You can charge them rapidly. They have a higher round-trip efficiency compared to lead acid. Lifetime is much longer, over at least 3,000 cycles, which is over 10 years. They degrade, say, linear. So sometimes lead acid batteries, they show a sudden death failure, as we call it. And particularly LFP batteries, they have a very low risk for catching fire, which is unlike some car batteries. The lithium is not toxic, and so on and so on. Now, some drawbacks. You need more electronics, and we'll come back to that in a minute, but basically you need a battery management system to monitor the voltage and the currents of each cell. That battery management system can be in the battery pack or in the charge controller, or can be separate. And that makes, of course, the system more vulnerable. It's more complicated. It's also more expensive, of course. Lithium batteries are expensive, but the prices are declining. And the recycling is not yet available for lithium batteries. So here, some comments about the battery management system. On the left-hand side, you see the situation that in the blue top here, you see this battery. It looks like a normal battery, although it is not lead acid, but this is lithium. And in this, under this blue cover, there's lots of electronics. I've shown it here with wires to each on the individual cells to measure temperatures, charging currents, and so on. The advantage of that you can use a normal charge controller for this battery. The other alternative is that you have a charge controller with the BMS included, and then in this case you can replace the battery pack, and you don't have to throw away the BMS. So this on the right hand side, that's usually in these solar kits. It's included in one package. Now, for comparing some costs, here I made a comparison between lithium and lead acid, but must say at 30 degrees C, because the advantage comes in at lithium. So on the left-hand side, we see here a lead acid battery with the various capacities and the price. And we see here the lithium batteries with either, this one has a BMS inside the battery pack. And in this case, this without a BMS. And you see the number of cycles is higher. This manufacturer claims even more cycles. I have a question mark there, but nevertheless, the lifetime will be longer than compared to lead acid. Prices are also higher, and you can see on this battery is definitely double the price over lead acid. And if you do the calculations for life cycle cost per kilowatt hour, then you can see that lithium is getting there. In this case, of course, you need to add the cost for the BMS. In this case, it's already included, but double the price. And who guarantees that this battery is still running in 10 years' time? So it's not straightforward. We're getting there. But for now, I think lead acid is still around for the time to come. If we have this conversation in a few years' time, then the numbers will be different, and then we'll talk about it again. Now, at the end here, this is the end of my presentation. Thank you very much, and all the best to you.